Good evening, everyone. Welcome to the fourth interactive session of NPTEL Gig platform. Today, we'll be looking at engineering mathematics, particularly at Fourier series and partial differential equations. I am Naresh, a research scholar in the Department of Civil Engineering at IISc Bangalore. For the benefit of those people who are attending my session for the first time, so you're free to interrupt anytime if there is any question. You can also type in the chat box, or you can raise your hand and you can unmute and talk. So we want to have this as a very interactive session, so it is very helpful for all of you. And right now the strength is also very less, so we can have it one-to-one, no problem. And after the session, if you have any doubts, you can post it in this team. So you can join this Google group. So I'll paste the link to the group in this Q&A section. You can just click the link and then you can click join group. So that will add you to the group. And if there are any doubts regarding the content that I covered in this session or any other content for GATE in general, you can post it there. And you can also provide your feedback about my session in this group. So I will also be uploading all the presentations that I use in these sessions and the link to the recording of the video so that you can refer it after the session is over. So let us quickly get started. So partial differential equations are very important in engineering, as all of you know. They govern various physical phenomena, starting from equilibrium of deformable bodies, transport phenomena, vibrations, and so on. So what they are characterized by the presence of more than one independent variable. So when we have functions of multivariate functions, say if you have u as a function of x, y, and say time also, derivatives with respect to all these independent variables will appear in a partial differential equation that you know. And what are those derivatives? They are partial derivatives. They're not total derivatives. And what is the order of a partial differential equation? So order of a partial differential equation is the highest derivative. So this is the order. And what is the degree? Degree is the power to which the highest derivative of a PDE is raised to. So these are very similar to what we have in ordinary differential equations. To solve a partial differential equation, we typically require boundary conditions and initial conditions. So these are important apart from the differential equation itself to solve the problem. We'll look at it in the problems that we solved today. And if the partial differential equation is linear, what is linear? Linear means order is equal to 1. Not only that, the power of all the terms involving y, involving the dependent variable and its derivatives is 1. So they are all linear. You have so y appears just as y multiplied by probably a constant or so. Y dash dou u by say dou y by dou x. These appear just as it is. It doesn't appear inside a cos or sine function. It doesn't appear as an argument of some other function. So you know all of this. Then we can classify partial differential equations as elliptic, parabolic, and hyperbolic. So this is a special class of partial differential equations called quasi-linear second order partial differential equation. So the name may sound a little weird, but don't worry, it is just a terminology. We'll see what it is. In GATE syllabus, so partial differential equations is a very vast topic, but what we have for GATE is very, very small. So you have So Fourier series, we look at it today. We only have partial differential equations that can be solved by the separation of variables. So, and what are they? One is the 1D diffusion equation, and then we have 1D wave equation, and we have the 2D Laplace equation. All these are partial differential equations with two independent variables. We also have the first order wave equation. We look at it at in a later session. So let us get started with Fourier series first, then we'll go to partial differential equations. So what are Fourier series? Fourier series are used to approximate periodic functions. So what are periodic functions first? So if you have a function f of x satisfying f of x, suppose you have a real valued function. What is a real valued function? It takes a real number and gives out another real number. So a function which satisfies f of x plus p is equal to f of x for all real numbers, for all x belonging to real numbers, is said to be periodic function with the period p. So standard examples, sine of x is equal to sine of x plus 2 pi. So what is the period of this? So p is equal to 2 pi. This holds for all real numbers. And similarly, sine of 2x is equal to sine of 2 into x plus pi. So what is the period here? P is equal to pi. So if you replace x with x plus p and the function remains the same for all real values of x, then it is a real periodic function. So you can have infinitely many periodic functions. You can have things like this, a square wave, which extends everywhere in the real line, but it is periodic. So you take the value here and you take it at some point after. So this is the period of this function. So there can be infinitely many such functions possible, but to approximate them, we use Fourier series. And they're also important in the context of solving partial differential equations. We'll see that in an example today in one of the previous year gate problems. So as I said, what is the period of a function? Period is any number p that satisfies f of x is equal to f of x plus p for all real numbers x. Now, we should be careful in differentiating between the fundamental period of a function and a period of a function. For example, if you take sine of x plus 2 pi is equal to sine x for all x. However, sine of x plus 4 pi is also equal to sine x for all x. Similarly, sine of x plus n pi is equal to 2n pi is equal to sine x for all x belonging to real numbers and n belonging to natural numbers. Therefore, what are all the periods of sine? 2 pi is a period, 4 pi is a period, 6 pi is a period, and any even multiple of pi is a period for the sine function. But what is the fundamental period? The smallest number which satisfies this is called the fundamental period. So 2 pi is the fundamental period of sine x, whereas 4 pi, 6 pi, 8 pi, these are all just periods. So this distinction is important. Now let us take the function sine 2x. We know that sine 2x plus 2 pi is equal to sine 2x. But what is sine 2x plus 2 pi? Sine of 2 into x plus pi is equal to sine 2 pi. So what are all the periods of sine 2x? You can have pi is a period. Suppose I make it 2, you get sine 2x plus 4 pi, which is again sine 2x. 2 pi is a period, 3 pi is a period, and so on. So these are all valid periods. This is the fundamental period. Now, let us consider, let us consider functions with period 2 pi, right? So suppose f of x is a function with period 2 pi. So remember, 2 pi doesn't have to be its fundamental period, it is just a period. So if you shift the function by 2 pi, nothing changes. We get the same function back. So that is what it means in this case. Now let us say this, right? So construct this series. Suppose we construct this series. So you know what a series is. Let us call it, say, a naught, which is a constant, plus a1 cos 1x plus a2, b1 sin 1x plus a2 cos 2x plus b2 sin 2x plus, and so on up to an cos nx plus bn sin nx, and you can keep adding terms as it is till infinity. So this is nothing but a naught plus n going from 1 to infinity, an cos nx plus bn sin nx. Now let us see what are all the periods for this term. Periods are 2 pi, 4 pi, and so. Let me use a different color. For the first term, the periods are 2 pi, 4 pi, 6 pi, and so on. The second term is the same, 2 pi, 4 pi, 6 pi, and so on. What are the periods of cos 2x? Could anybody unmute and tell? Simple, right? Yes? If you shift x by something, cos 2x should remain cos 2x. So what are all the periods for cos 2x? Feel free to interact. It will help you. You can be wrong. Don't hesitate to tell the wrong answer also. You can be wrong. It's okay. You can interact. Yes? Okay, so cos 2x plus 2 pi is the same as cos 2x. If you take 2 commonly out, you get cos of 2 into x plus pi. So if you replace x with x plus pi, nothing changes. Therefore, pi is a period, 2 pi is a period, 3 pi is a period, and so on. Same for this term. Now, what about these two? So if you take 3 cos 3x, you will have 2 pi by 3 as a period, 4 pi by 3 as a period, and so on. So for this, the periods are 2 pi by n, 4 pi by n, 6 pi by n, and so on. Now, what is the common period for all these? So here you have 2 pi, here you have 2 pi, here you have 2 pi, and here also you will get, and you get n into 2 pi by n. So there also you'll get 2 pi. So the common period for all the terms in this series is 2 pi. Therefore, the series is 2 pi periodic. This summation is 2 pi periodic. So this has a period 2 pi. Now, if the series converges, say, you know about convergence, right? So when do you say series converges? If you take subsequent partial sums, you take first term, you take then the second term, you take then the third term. If you take the sums, the sequence of the nth partial sums converges to some number. So if you take 1000 terms of the series, you get some number n. and you take 1001 term of this series, you get some number n plus delta. So if this delta can be made arbitrarily small by taking a sufficiently large n, then you say the series converges to that number n. So if the series converges to a function f of x, then f of x will also be periodic with the period 2 pi. Why? Because everything on the right hand side is 2 pi periodic. So we will have f of x is equal to f of x plus 2 pi. So this is what we basically use in Fourier series. If we have a 2 pi periodic function, and if such a series converges, if the coefficients of this are such that the series converges, then we can take such a function f of x and express it as a summation of sines and cosines. And also this constant term a naught. So this is the heart of Fourier series. How do we determine the coefficients a naught, a1, a2 for a given function? So this function, if it is given, these are known as Fourier coefficients. So the proof that this series converges to f of x is difficult. It is very advanced. It is in advanced mathematics books. But you can see it converges. It is easy to show it converges, but what it converges to, that is a bit involved. That comes in advanced mathematics books. So how do we find out? How do we compute the Fourier coefficients? For this, we use the property of orthogonality. Right? So if you take, for example, so it is simple. So suppose you consider this integral, right? Minus pi to pi cos mx cos nx dx when m is not equal to n. And we'll also consider the case when m is equal to n. So this, using the cos formula, you can write it as cos of m plus nx minus, sorry, this is cos, right? Yeah. So it is cos of m plus nx minus cos of m minus nx by 2 dx. Minus pi to pi. But cos mx is, this is just m plus n is something, m minus n is some integer, this is some integer, this is some integer. Their signs don't matter because cos is an even function. Whatever this integer is, we know that 2 pi is a period. So whatever this is, it is periodic. So 2 pi is a period of the integrand. In that case, if you take any cos function, if you integrate it from minus pi to pi, for example, if you take cos, so if you take cos 1x is something like this. Cos 2x is something. So cos 2x is something like this. And you can have cos nx. So all these have equal areas above and below the x-axis. So when you integrate cos m plus nx from minus pi to pi, all of them vanish. So this is 0, this is 0. So the area above the x-axis cancels with the area below the x-axis. So when m is not equal to n, this integral is always 0. What happens in the case m is equal to n? If m is equal to n, then you can write it as minus pi to pi cos mx, which is nothing but cos square mx by 2. There's no by 2, cos square mx dx. But what is cos square mx? It is nothing but 1 plus cos 2mx by 2. How does this come? Use the formula for cos 2mx. Cos 2mx is 2 cos square x minus 2 cos cos 2x is 2 cos square x minus 1. You just rearrange it, you get this. Then again the same argument. Whatever m is, whatever m be, 2 pi is the period of this function. So if you integrate this from minus pi to pi, this part vanishes. And when you integrate this, what do you get? You get 2 pi by 2, this pi. Similarly, you can show that minus pi to pi sine mx cos nx sine mx sine nx dx is also equal to 0 if m is not equal to n and pi if m is equal to n. And minus pi to pi sine mx cos nx dx is always 0 regardless of what m and n are. So using these, what we do is just integrate on both sides, multiply by cos mx and integrate on both sides of this equation. Let us call this equation as equation 1. So if we multiply by cos mx and integrate on both sides, in one case, all the terms for which n is not equal to m vanishes and you get only one term that integrates to pi. Therefore, the Fourier formula is given by, where do I write it? I'll write it here. The Fourier coefficients are given by, for 2 pi period, for 2 pi periodic functions, the Fourier coefficients are given by an is equal to, because what do we have? Pi times an is equal to integral f of x cos nx dx from minus pi to pi. This side, when you integrate everything, all the other terms vanish, so you'll get a pi here. Let us bring it down. So you get a 1 by pi. Similarly, bn is equal to, using the second formula, right? It is pi when m is equal to n and all other terms vanish. Therefore, bn is equal to 1 by pi integral minus pi to pi f of x sine nx dx. And you also have this a naught term. What about the a naught term? Have an a naught term, right? So just integrate on both sides from minus pi to pi. Don't multiply by anything. This term definitely vanishes because all these are 2 pi periodic. This entire term vanishes. You just get a naught into a naught integrated from minus pi to pi. A naught is a constant, so just dx integrated from minus pi to pi is 2 pi. So you get 2 pi times a naught is equal to integral minus pi to pi f of x dx. Just bring the 2 pi this side, you get 1 by 2 pi. So these three formula is all that we need to solve any problem in Fourier series involving a 2 pi periodic function. But not all functions are 2 pi periodic. You can have an L periodic function. You can have a function with a period L. Any doubts until this point? Is there any doubt? Is everything okay? Okay, thank you. So if you have an arbitrary period, let us call the period as L. We make this transformation, right? You instead of so if you have a function with the period L, so it's just a small transformation. You get the Fourier coefficients as, so f of x is equal to f of x plus, let us take it as 2L so that you don't get a half everywhere. F of x plus 2L. In place of pi, you have L. So it is simple. In that case, you express the Fourier series as f of x is equal to a naught plus summation n equal to 1 to infinity an cos, it is 2L periodic function. So in place of pi, you need to get L. Therefore, it is n pi x by L. So when x is equal to L, you get cos n pi. So that is exactly the same. It is only a transformation. It is only a change of variable plus bn sine n pi x by L. So when x equal to 0, you get 0. And when x equal to L, you get cos n pi. So it is the same thing. You just scale it by L so that instead of being pi period, 2 pi periodic, it is 2L periodic. That's all. In place of pi, you need to get L. So this is the transformation. And what are the Fourier coefficients? They are simple. So exactly the same formula, very similar formula, just replace pi with L. So A naught is equal to 1 by 2L integral minus pi to pi f of x dx. An is equal to 1 by L integral minus pi to pi f of x cos. Instead of nx, you have n pi x by L. N pi x by L dx. And Bn is equal to 1 by L. Sorry, did I write pi? All these should be L because our period is in L. So all these are in L. Minus L to L. This is also from minus L to L. Minus L to L. F of x sine n pi x by L dx. So that's all it is. Now we have the special case when f of x is an odd function. What does it mean? F of x is an odd function means f of x. So this is, let us call it case 1. It means f of x is equal to f of minus x multiplied by minus 1. So if you replace x with minus x, f changes sign. So it's like odd function. Say odd powers of minus 1, right? So f of x equal to minus f of minus x. So sin x is an odd function, tan x is an odd function, cosine x and secant x are even functions. So x square is an even function, x cube is an odd function. So if you have an odd function, then what happens to this integral? An is equal to a naught is equal to 0 for all n. Why? Because if you inside this integral, you have an odd function. If you integrate from minus L to L, the area below the x-axis will be equal to the area above the x-axis, and it will be 0. And what about the second case? So this is an odd function. So this is an odd function. This is an even function. So together it is an odd function. So if you replace here x with minus x, this will become minus f of x, but this will remain just cos n pi x by L because cos of minus x is cos x. In that case, the entire integrand has shifted its sign by a minus 1. So when you integrate from minus L to L, the integrand will just be the area below the x-axis will be equal to the area above the x-axis. So an will be 0. So you only have f of x is equal to summation bn sine n pi x by L. And bn is as usual given by this. There's no change in that. And in the second case, if you have f of x is an even function. In this case, what happens? So even function means f of x is same as f of minus x. So if you take the axis, if you have a function like this, f of x is f of minus f of x. F of minus x is f of. So if it is like this mirror image, it is an odd function. And if you take a function like this, and it's a mirror image like this, it is just equal, it is symmetric about the y-axis, then it's an even function. In that case, bn's are equal to 0. Why? Same reasoning. You have f of x is an even function, sine is an odd function, so the entire integrand is an odd function. So when you integrate from minus L to L, it vanishes. That's all. In this case, you get f of x is just summation of a naught plus an cos nx n pi x by L. That's all. So hope that is enough. Let us solve this problem today. Is there any doubt before we get to this problem? Do you have any doubts I can clear? Any doubts? Is that clear? I don't see any response. Could anybody unmute and say if it is okay? Okay, thank you. So let us look at this function. We are given f of x is equal to cos power 4x. And we are asked to find out the numerical value of f4 plus f5. And we are actually given the form of the series. So note that you are given a cosine series. So why? Cos power 4 is an even function. So directly, why is it an even function? Yeah, the power is 4 and also cos is even. So if you just substitute minus x here, you will just retain f of x equal to f of minus x. Therefore, it's an even function, which means all the sign coefficients, Fourier sign coefficients are 0. Therefore, the Fourier form is only this. Now let us look at, let us evaluate this, right? Let us find out the Fourier coefficients an. So an, what is an? So a naught is also 0. That also you can. So make use of what is given in the question. So this may look like an extra information because given f of x, we can find a naught b1, a naught bn and an all by ourselves. But make use of the fact that here a naught is equal to 0 and bn is equal to 0. In case you forget it is an odd function or even function, just make use of this. So don't spend time computing a naught or bn in the actual gate exam because we have limited time. Directly go to an. What is an? Quickly. So what is the period of this function cos nx, or rather cos 4x, cos power 4x? We don't need to know whatever the period is. We know at least it is 2 pi periodic. So let us, right? We don't need to know the fundamental period. So you can integrate from minus pi to pi. You can integrate from minus 2 pi to 2 pi. So let us integrate from minus 2 pi to minus pi to pi. So an is 1 by pi integral minus pi to pi f of x cos nx dx. Now let us write this as 1 by pi integral minus pi to pi. Any idea? How do we handle cos power 4x? Yes. How do you usually handle powers of trigonometric functions in integrals? That's very important, right? How do you usually handle the powers of trigonometric functions in integrals? I can interact.
By substituting t for that and then.
Yes, but that will not help here, right? You can substitute t, but you will just get t power 4 and dx. What will happen to dx? Dx will still remain dx, right? It will not transform to anything in terms of t. So let me tell you. So you can write this as cos square x the whole square cos nx dx. Is that okay?
Yes.
Yes. Now let's go to the next step. Again, let us use the half angle formula. So you know that cos 2x is equal to 2 cos square x minus 1. So what is cos square x? It is 1 plus cos 2x by 2. So what do we have in the integral? We have cos square x. In place of cos square x, substitute this. So you get an is equal to 1 by pi integral minus pi to pi. You have 1 plus cos 2x by 2 the whole square cos nx dx. So 1 by 2 square, let us take it out. We get 1 by 4 pi. 2 square is 4 minus pi to pi. Let us expand this. So this is a plus b the whole square. So we get 1 plus 2 cos 2x plus cos square 2x cos nx dx. Now let take 2x as some t or whatever. What about again substitute this for this term? Right? Substitute this for this term. So what do we get? 1 by 4 pi integral minus pi to pi. We get 1 plus 2 cos 2x. There is no change. Here what will happen? Here it will become 1 plus cos of 2 times 2x, which is cos 4x by 2 multiplied by cos nx dx. Now, very simple. Just do the multiplication. I'll do it in the next page. An is equal to 1 by 4 pi integral minus pi to pi. What is the first term? 1 multiplied by cos nx. So you get a cos nx. What is the second term? 2 cos 2x multiplied by cos nx. Let it be 2 cos 2x multiplied by cos nx. What is the third term? It is, so let us take it as 1 by 2. 1 by 2 multiplied by cos nx. So we get a 1 by 2 multiplied by cos nx. What is the fourth term? 1 by 2 cos 4x cos nx. So we get 1 by 2 cos 4x cos nx dx. Quickly, you don't need to integrate. Directly, you know cos nx. What is the period of cos nx? It is 2 pi by n, but 2 pi is also a period. So when you integrate it from minus pi to pi, what will happen? What is cos nx integrated from minus pi to pi? The area above x-axis will be equal to the area below the x-axis, right? Is that okay? Cos nx multiplied cos nx integrated from minus pi to pi is what? Is 0, right? Or if you can't, if in case you find it hard, you can also integrate it. So cos nx will become sin nx by n, and substitute the limits minus pi to pi. You will get sin n pi minus sin minus n pi. Whatever n is, sin n pi is 0. So the first term vanishes. Similarly, this is just a first term multiplied by half. So this also vanishes. What about these two terms? Remember, we talked about this orthogonality property, right? What did we say? Cos mx cos nx is equal to pi if and only if m is equal to n. And for all other cases, it is 0. So cos mx cos nx, if you have such a form, it is equal to 0 whenever m is not equal to n. In this case, what do we have? So for all n which is not equal to 2, this term vanishes. Therefore, let me write it. So suppose n equal to 2. What is a2? A2 is, you get 1 by 4 pi. You get cos 2x cos 2x. And what is cos 2x cos square 2x? It is, we saw that cos mx cos nx is integrates to pi. So again, there's a 2 multiplied by pi. Plus, you have this. In this case, n equal to 2. This term they cannot contribute because you have cos 4x cos 2x. M is not equal to n. So this term vanishes in the case n equal to 2. So I have plus 0 plus 0 plus 0. So all the other terms are zeros. So a2 is equal to 1 by 2. And now suppose n equal to 4. What is a4? First term vanishes. So you have 1 by 4 pi. The first term vanishes. Second term, you have cos 2x cos 4x. So 2 is not equal to 4. So that term also vanishes. This term vanishes. And here you have plus half times integral cos square 4x. Integral cos square 4x, we saw that if m equal to n, it integrates to pi. So if n is equal to 4, you get a4 as pi by 8 pi, which is 1 by 8. And for all n not equal to 2 and n not equal to 4, an is equal to 0. So I hope that is clear. Therefore, what is what is the series? F of x is equal to a0 is 0, a1 cos 1x, a1 is 0, a2 is half, plus a3 is 0, plus a4 is 1 by 8 cos 4x, plus A5 is 0, plus A6, and everything else is 0. So this is F4, this is F5. And what is asked in the question? We are asked F4 plus F5. So F4 is equal to 1 by 4 or 1 by 8. F2 is equal to 1 by 2. F5 is equal to 0. And all other ends are 0. So F4 plus F5 is equal to 1 by 8, which is 0.125. So the correct answer to this question, the numerical value of F4 plus Fy rounded off to 3 decimal places is 0.125. Any doubts? Is that clear? This problem, I hope, is it clear? Okay, thank you. Let's go to the next section for today. The next section, okay, since you said it's clear, in case any of you have doubts, as I said, please feel free to contact me in this group. You can post your query in this group. You can also, I will be uploading the live this one onto YouTube. You can also post as a comment, whatever it is, whichever way you want, you can contact. So now the next section is solution of partial differential equations by separation of variables. There are only 4 steps if the partial differential equation you are looking at admits a variable separable. If it admits the separation of variables, there are only 4 steps. So suppose you have some partial differential equation, say second order. Yes. So if you have a second order partial differential equation, it is second order linear partial differential equation. It is of the form A dou square u by dou x square plus B dou square u by dou x dou y plus C dou square u by dou y square is some function of x, y, u, dou u by dou y, and dou u by dou x. So typically you have a partial differential equation like this where A, B, C are real numbers. So in the special case, if you have this b square minus 4ac is less than 0, you get an elliptic partial differential equation. B square minus 4ac equal to 0, you get a parabolic partial differential equation. B square minus 4ac greater than 0, you get a hyperbolic partial differential equation. These names really don't matter. They are just names. They are just names that are useful for classifying the kind of solution these partial differential equations have. For example, if you take elliptic problems, the characteristic is that if there are sharp gradients, if there is something sharp imposed on the domain, it gets smoothened out. On the other hand, parabolic problems deal with some kind of decay. So there is something in time. There is something. So at time t equal to 0, you have something, and it slowly decays exponentially. That kind of problems you have parabolic PDEs. For example, cooling, Newton's law of cooling, those kinds of things. And hyperbolic have to deal with oscillations in time and space. So wave equation comes under hyperbolic. So the first step is to separate the variables. Suppose you have 2 variables, u of x comma y. You know, partial differential equations deal with multiple independent variables and one dependent variable. So the trick is you assume that it admits a product form of solution, f of x, g of y. Substitute into the governing equation and then just satisfy the boundary condition and solve the problem. That's all. So separate the variables, substitute into the governing equation, then you will get certain boundary conditions. So satisfy them. Then what does this mean? Construct the complete solution. We'll look at it when we solve the problem. We'll look at it, and then you enforce the initial and boundary conditions. So what about 2D Laplace equation? What is the Laplace equation? So Laplace equation is, this is called the Laplacian operator del square u is equal to 0. That's all. This is called the Laplace equation in 2D. This del square operator means dou square u by dou x square. This is nothing but these two are equivalent. Dou square u by dou square plus dou square u by dou y square is equal to 0. That's all. This is called the 2D Laplace equation. Now, how do we solve this by separation of variables? You assume u as a function of x and y is of this form, f of x, g of y. Just substitute it back into the governing equation. You get? So this can be treated as a constant while differentiating with respect to x. So only f will get differentiated. You get f double dash of x, g of y, plus. Similarly, when differentiating with respect to y, you can treat f of x as constant. You get f of x, g double dash of y is equal to 0. Now we have the trick, right? Divide y of x, g of x on both sides. Of course, this assumes f of x, g of x is not equal to 0 because you can't divide by 0, right? So assuming this, you divide it on both sides by f of x, g of x, you get here g of y, g of y. In the first term, g of y will get cancelled. So you get f double dash of x by f of x plus g double dash of y by g of y is equal to 0. Can you see something here? Do you get any idea here? How do you solve this? You have one term that only depends on x. This depends only on x. And this depends only on y. What is the function? So both of them are equal to some function. But what is that function which is a function of x only and it is a function of y only? So if you take sin x is a function of x, but it's not a function of y. And if you take some other e power y is a function of y, but not a function of x. Can you tell me one function which depends on x only as well as y only? Constant, right? So both of them should be equal to some constant. So this is equal to, say, a constant. Let me put it this way. Yeah. So let this be equal to some positive constant k square. And what should this be equal to? This should be negative of this. That's all. So square is just to denote that it is positive. You can take it as just k also, just k greater than 0. One of them is positive, the other is negative. That's it. So if this is the case, now we can split it into two independent, so where k is some real number. K is some real number. Now you can split it into two different ODEs where you get f double dash of x by f of x equal to k square is one ODE, and g double dash of y by g of y is equal to minus k square is another. So let's rearrange. You just have to solve for two different ODEs, which are f double dash of x minus k square f of x is equal to 0, and g double dash of y plus k square g of y is equal to 0. And for these, you know the general form of the solution, right? If k square, in this case, suppose if it is of this form, we can also have the minus sign here. That is determined by the boundary conditions. So this is one way you can solve the problem. So the general form of the solution is a e power kx plus b e power minus kx and so on. So just substitute, and if you have any boundary conditions, obey that, enforce that, and then can solve the problem. So it may look a little complicated, but when we solve the actual problem, it will become very simple. For the diffusion equation, it's the same thing. So the diffusion equation is this. You have dou u by dou t is equal to, I think, c square or c, depends on how we call it, c square dou square u by dou x square. Same thing, just take u of So u is a function of x and time. So u of x comma t, you can take it as some f of x multiplied by g of t. Again, substitute into this, you get. So this is a function only of this derivative is with respect to t. You can treat f of x as a constant. And time derivatives, let me put a dot on top. G dot of t is equal to c square f double dash of x g of t. Again, separate the variables. You get f of x, sorry, g dot of t by c square g of t is equal to f double dash of x by f of x. This is a function only of t only. This is a function only of x only. So both of them should be equal to some constant. Let us call it some k square or whatever. Then the same procedure, split it into two ordinary differential equations and solve them separately and enforce the boundary conditions. Similarly, you have the 1D wave equation, which is also very simple. Dou square u by dou t square is equal to c square dou square u by dou x square. In all these cases, it also helps to look at the type of the equation. So here a is equal to 1, c is equal to 1. The mixed derivative term is not there. So b square minus 4ac is minus 4. So this is elliptic. And what about this? Here you have a is equal to 1, b is equal to 0, c is equal to 0. So b square minus 4ac is 0. So this is parabolic. And here a is equal to 1, a is equal to 1, and a is equal to 1, b is equal to 0, and c is equal to minus c square. So b square minus 4ac is 0 minus c square. So it is c square, which is positive. So it is hyperbolic. But the trick is still the same. You assume u of x comma t as f of x, g of t. Treat f as constant while taking time derivatives and treat g as constant while taking space derivatives, x derivatives. So you get f of x, g double dot. So double dot means time derivatives. Double dot means second derivative with respect to time is equal to c square f double dash of x, g of t. Rearrange, you get g double dot of t by c square g of t is equal to f double dash of x by of x. This is a function of t only. This is a function of x only. Therefore, both of them should be equal to some constant k square or omega square, whatever it is. The next step, as usual, is enforce the boundary conditions and solve the problem. So to demonstrate it, let us quickly look at this will come later on because this requires polar coordinates. We'll look at this diffusion problem. So we have a 5 centimeter long metal rod AB initially at a room temperature of T0. Thereafter, the temperature at both the ends is maintained at 0 degrees Celsius. Neglecting the heat transfer from the lateral surface of the rod, the heat transfer in the rod is governed by the 1D diffusion equation. So they have given the equation. This is the parabolic 1D diffusion equation, where D is c square, what we called as c square, that is D, is given as 1 centimeter square per second. The temperature distribution in the rod is obtained as this. So they have also given the form of the solution. We'll quickly see why this form comes. Okay. So let me. If there are any doubts, as I said, please feel free to interrupt because I didn't pause here, assuming you all understood this separation of variables, right? It's just simple. So yeah, so if you have this is the form of the solution. And what is asked? We are asked to find out the value of beta rounded off to 3 decimal places. Okay, so let us solve the problem. So we are given dou t by dou small t is equal to capital T times dou square t by dou x square. Let us assume the temperature distribution as a function of the space x and the time t is given as some f of x times g of t. Substitute into the governing equation. So while taking time derivatives, you can treat x to be a constant. So you get f of x g dot of t is equal to d times. Here the derivative is on f because g can be treated as a constant. F double dash of x g of t. Separate the variables. We get f of x by f double dash of x. Sorry, this side we have g of t, right? So f of x will be f of x goes to the other side. So we get d dot of t by d g of t is equal to f double dash of x by f of x. So this is a function of t only. This is a function of x only. Both of them are equal to some constant, say beta. No, not beta. Let us call it k. Some constant k. What else do we have? So let us separate the governing equation. So we get one equation, this f double dash of x minus k times f of x. So this can be okay. We'll go systematically. F minus k times f of x is equal to 0, and g dot of t minus d k times g of t is equal to 0. Let us call this equation as 1 and this equation as 2. How do we solve equation number 1? Let us assume there is a solution of the form. Assume some a e power lambda x plus b e power minus lambda x. You know this, right? So if you have so k is some parameter, k is some real number. So you know this satisfies the governing equation. This is a homogeneous second order linear ordinary differential equation. So if you substitute this into the governing equation 1, so you just substitute this in 1, what do you get? You get f double dash of x. What is f double dash of x? So e power lambda x. You'll get a lambda square e power lambda x plus minus lambda. So plus b lambda square e power minus lambda x plus what do we already have? We have not a plus. You have a minus k e power lambda x plus b e power minus lambda x is equal to 0. E power lambda x and e power minus lambda x are never 0, right? They are always greater than 0. When x equal to 0, they are 1, and when x equal to infinity, it depends on plus or minus. So you can take a e power lambda x plus b e power minus lambda x commonly out, and you get lambda square minus k is equal to 0. If k is greater than 0, then lambda is equal to root of k. So what is fk of x? Fk of x is a e power root kx plus b e power minus root kx. But what will happen if what are the boundary conditions we have? So we have separated the variables. We have solved for one of the functions. But what is the boundary condition? What is the boundary condition? It is given that thereafter the temperature at both the ends is maintained at 0 degrees Celsius. It means u of for all time t, u of x comma t is equal to 0 at x equal to 0 and x equal to L. That is u of 0 comma t is equal to 0 and u of L comma t is equal to 0. We have already separated the variables, so it should not depend on t, which means fk of 0 is equal to 0 and fk of L is equal to 0. So what does this give? This gives that a plus b is equal to 0, and the other equation gives that a e power root kx root kl plus b e power root kl minus root kl is equal to 0. So this is a 2x2 system. If you solve, what do you have? Here you have 1 e power root kl, e power minus root kl, and this system. So if you take the determinant of this is never 0. Therefore, a is equal to 0 and b is equal to 0. But this is a useless solution. Why? If a is equal to 0, b is equal to 0, then fk of x is always 0, which means u is equal to 0 is the solution. But that is not what we want. We want a non-zero solution. So we know that if you just substitute 0 on both sides of this equation, the temperature is 0 everywhere at all times. That's the obvious solution, but that is not what we want. We want to get a solution that satisfies the initial conditions. Therefore, the determinant of this has to be equal to 0, which means our assumption that k greater than 0. We assume k greater than 0, right? So if k greater than 0, lambda is equal to root k. So that assumption is wrong. Therefore, k is less than 0. If k is less than 0, what will the governing equation become? So if k is less than 0, let us call k is equal to some minus omega square. Omega square is always positive, so minus omega square is negative. The governing equation will become f double dash of x minus kx, so minus into minus omega square, which is plus omega square f of x equal to 0. All of us know the general solution to this problem, which is f of x is equal to a cos kx, a cos omega x plus b sine omega x. Now enforce the boundary condition. F of x equal to 0 is equal to 0. What does that mean? This term will vanish. So a cos 0, which is 1, a is equal to 0. And what about the other boundary condition? F of x equal to L is equal to 0. A is already 0. So we get b sine omega L is equal to 0. What does this mean? Omega is equal to n pi by L for n equal to 1, 2, and so on. If b not equal to 0. Again, if a equal to 0, b equal to 0, we get the useless solution, which is the temperature is 0 everywhere at all times. But that is not what we have. We have an initial temperature distribution at T naught. So b is equal to, so b doesn't matter. We only have omega is n pi by Lx. So call Fn of x as Bn sine n pi x by L. What is omega here? Omega is n pi by L. What is k? K is root omega. K is minus omega square. So it is minus n n square pi square by L square. Okay. Now we have the other equation here in terms of g dot of t minus d k g of t equal to 0. So we need to solve for this. So we have g dot of t minus k d g of t is equal to 0. But what is k? K is, what did we get k as? K is minus n square pi square by L square. So this corresponds to g nth value, right? So we get minus into minus plus d n square pi square by L square g of t equal to 0. Now let us call this as some m. We get there's an n here. Gn dot of t plus mgn of t is equal to 0. What is the general solution to this? So this is a linear first order ordinary differential equation. You know this, you can multiply by an integrating factor, which is say e power mx on both sides, e power mt g dot of t plus m e power mt gn of t is equal to 0. So you can take, so this is nothing but derivative of e power mt. So you get d by dt of e power mt g of t is equal to 0, which means this entire thing is a constant. So g of t into e power mt is equal to some constant c1. Therefore, g of t is equal to So mine C1 e power minus mt, where m is this thing. So this is Gn of t. Now let us combine the full solution. So you get, we just got, so for every n, fn of x, Gn of t is a solution. And for linear, so if you remember here, I said while solving, construct the complete solution, right? So suppose you have two independent solutions, then for linear differential equations, doesn't matter if it is ordinary or partial. If for linear homogeneous differential equations, if u1 of x and u2 of x are solutions, then some random combination of u1 of x plus u2 of x is also a solution. Right? You know, all of you know this. That is why we wrote f of x as a cos omega x plus b sin omega x, because cos omega x also satisfies the equation, sin omega x also satisfies the equation. Same thing with the e power lambda x also. So in this case, if you have two, it's just a plus b. If you have three, it is a u1 of x plus b u2 of x plus c u3 of x and so on. Now, if you have n such values, for every n, fn of x, gn of t is a solution. Therefore, the complete general solution is what? T of x is summation of, you can have some coefficient, say Tn or something. Tn, sorry. Let it be Tn. Fn of x, Gn of t is a solution. So Fn of x, Gn of t, n going from 1 to infinity. So just substitute the values, you get summation n going from 1 to infinity. What is the thing they used? What is the variable? They use Cn. So let us also use the same thing. So Cn is some combination, some coefficient. Cn times, what is Fn of x? Sine n pi x by L. And what is Gn of t? Gn of t, we just got it as this, some constant multiplied by e power minus mt. So that constant this is also unknown constant, that's also unknown constant. So it is nothing but e power minus mt. What is m? What is m? M is this d n square pi square by L square. So minus d n square pi square by L square times t. This is the complete solution to this problem. Did we get the complete solution? No, we don't know Cn's, right? So how do we find Cn? Note what we have just got. So it is given that at time t equal to 0. Yeah. Initially, it is at a room temperature of T0. So what does that mean? So this is T of x comma t. T of x comma t equal to 0. When time t is equal to 0, temperature is T0. This means that in place of t, you substitute 0. So you get T0 is equal to summation n going from 1 to infinity, some Cn sine n pi x by L. This term vanishes. Can anybody recognize what is this? Yes. This is the Fourier series, Fourier sine series, right? This is just the Fourier sine series of this function T0. T0 is a constant function, and Cn's are the coefficients, Fourier coefficients. How do we get Cn? Cn is nothing but So simple. So Cn is nothing but integral T naught side n pi x by L dx. 1 by L, 1 by L minus L, 1 by 2L, right? 1 by 2L, 1 by L minus L to L. So this is just simple. T naught is a constant, and this integral, sorry, this. So if you assume that the it's an so you have from 0 to L, it is maintained at T naught. So this is x equal to 0, this is x equal to L. Here it is maintained at T naught, and you have a sine series. It means from minus L to L, you have minus T naught. That is what it means. So therefore, you can integrate this as integral 0 to L. So this, so suppose this is a period, it is an L periodic function, then you can take, so if it's an L periodic function, then you integrate it from 0 to L. And here you will have period by 2. So when you integrate from minus L to L, you get L. When you integrate from 0 to L, you get 2 by L. 1 by L by 2. By L by 2. So you get something like 2 by L integral T naught 0 to L sine n pi x by L dx. So this, if you integrate, you'll get cos x by L by n pi and all. But what is important is if n is odd, the integral vanishes. And if n is even, integral, sorry, if n is odd, Cn is not 0. And if n is even, you are integrating over a period, right? If n is odd, you are integrating over half a period. So in that case, you will get some value. And if n is even, Cn equal to 0. So which means all the odd terms of the series will only remain. So that is what is given in the question. So you might have wondered why it is 1, 3, 5, and so on, and not 1, 2, 3, 4, 5. The reason is this: you are having a rod. You are assuming it is periodic with a period L, and if the period is L, what should come out of the integral? It is 1 by L by 2, which is 2 by L. When you integrate from 0 to L, remember this is a 2 pi periodic function. So n pi x by L is 2L periodic. So when you integrate from 0 to L, this is not 0. It is whatever it is. You just integrate it, you get some cos n pi x by L by n pi by L, and you get LL cancel and whatever it is. That will not cancel out unless it is n is even. So if n is even, you are integrating over a complete period. So the region on top will cancel with the region on bottom and it vanishes. Otherwise, the region on top will remain. So otherwise, you'll get some value which is actually L. And if n is even, all the even terms vanishes. Therefore, in the summation, you don't have any even terms. You just have 1, 3, 5, and so on. So as the last step, what did we have in the exponent? We have minus d n square pi square L by L square t. Just compare this expression with what is given here. So e power minus beta n square t is nothing but this is the same, right? This is the same. L is 5. L is 5. N pi by Lx is the same. Cn, in place of Cn, you have some combination. That is also fine. And here you have minus d n square pi square by L square t. So just equate both. If the exponents are equal, so you get beta is equal to d n is not equal to 0. So n gets cancelled on both sides. We get n d pi square by L square. What it is, d it is given as 1 centimeter square per second. So 1 centimeter square per second. And what is pi square? Pi square is just pi square that you can take it in the calculator. And L square is 5 centimeter the whole square. So it is 5 centimeter the whole square. So what is the unit of d? What is the unit of beta? Beta is per second. So beta in per second is what? That is what they have given. It is just pi square by 25. So you can evaluate what is pi square by 25. What it is? Let me check. So you have pi into pi divided by 25. So the answer is 0.3947. So this answer is 0.395. So that is, yeah, we have slightly past time. Is that okay? I hope you all got what it is. I'll be uploading the presentation in that group, so you can refer to it. The steps are there. I have gone fairly sequentially. So the steps are there. You can refer it. Yeah, I'll wait for some time. If you have any doubts, you can ask. If you have any feedback, you can provide. If you get some other doubts after referring to this, also you can post in that group. I will get back to you. Or I'll also share the YouTube video link. You can also post as a comment to that. Yes, if you have any doubts, you can ask. Is everything okay? Okay, I'll wait for just say 2 minutes or so. If you have any doubts, you can feel free to ask now. If not, I'll end the session. Okay. Yeah, if you have any doubts, you can ask. So is everything okay? Okay, no problem. If you have any doubts, you can post in it. Now let me stop the recording and end the session right here. So thank you all for attending. We'll meet next week at 7 p.m. Okay.